going to call this the cereal demo. Cereal. And basically, we're going to take some what you want to do is take some observations as I am doing this. So this should be in your notes. So everybody should have their notes. Remember, Cornell style notes. And we're going to start with some, this morning I didn't get a chance for breakfast. My kids didn't want to get up this morning to go to school. My daughter has a 0-period PE class, so getting her up sometimes for PE in the morning is not great. So I'm going to put some, I need to get my cereal going, but because I want to get it a little faster today, I'm actually going to grind it up. Now, can anyone tell me, so one observation is I am taking the cereal and I'm grinding it up in the mortar. Why might I grind it up? Because I have to cook it. I like my cereal hot, so I'm going to cook it. Why do you think I'm going to grind this up in the mortar? Demo. Why would I want to grind this up in the mortar and pestle? What does that do for me when I start to cook it? I mean, compared to just a flake, when I grind this flake up, what am I doing to it? Well, what does it do when you grind it up? I start with this big flake. I make it smaller. I make a lot of little flakes, basically a lot of little particles. How do little things cook compared to big things? Faster. Why is that? Pardon? What? They have a smaller. Well, actually, you're kind of the right area. It's about surface area. The flake has a smaller surface area than all the little pieces, but by breaking up, because if I took the surface area of this and then broke it in two parts, what did I just do surface area? Well, I gained those two sections in the middle, right? And every time I break it a piece, am I increasing the amount of surface area? I haven't increased the mass, but every time I break it into a smaller part. So that's one observation. By grinding it up, I'm increasing surface area. So you might all want to write that down as an observation here. We're grinding it up and things like that. Now maybe you have one of these in your kitchen. It can be very useful in grinding, especially grinding spices up and things like that. Because by increasing the surface area on spices and stuff like that, you get a lot to kind of break up their flavor and things like that. Add. So we're going to start that. And you'll notice it's stirring. I should put on my glasses so I can see the setting. Okay, so that's on that. So we'll let that cook a little bit and see what happens on that. So we're going to start that. So you want to leave a gap in your notes. Leave a gap because we're going to come back to this. We're going to leave that cooking there on that, just like that. And get that in milk and heating up. All right, so we're going to start a little bit on our notes. Today we are going to talk about systems of measurement. I don't think we started this last time, did we? I don't think we talked anything about systems of measurement yet? No. So we're taking some notes. Remember, Cornell style notes, 1/3, 2/3. So we're going to take some notes today. We're also going to go over this lab form, things like that. We're going to talk a little bit about the demos we already did on that. After we do this one, we'll talk about some of those. And start a little lab that teaches how to make lab reports. Most of what's in this sheet has to do with writing lab reports. But first of all, systems of measurement. Our systems of measurement here. And we have the English system. Where's the English system we used? It's an older system, but where is the English system used today? Used in England? No. Where? Here! Yeah, basically we are the only ones who use it. Good old US of A. We are the only ones who use it. was a law actually in the 70s that was passed that said we were all going to be in the metric system, I think by sometime in the 80s.
Really?
Yeah, see how well that worked, didn't it? You know, I was like a teenager and stuff like that. They started making all the signs were in metric system and things like that. You know, everything was both systems on that. The thing about the English system was developed over time. Different measurements, different confusing rules. I mean, how many of you ever try to think, it's like, how many ounces in a gallon? And you're like thinking, how many pints and cups and quarts and, you know, you start, it gets very confusing. I mean, just so that, I mean, a foot. I mean, a foot. What's a foot? What was a foot? Where'd it come from? What? Yeah, he put his foot up. Yeah, his foot. But whose foot? Who? You know, let's think. Old times. Who was the most important guy around? The king. And usually we're talking about the king's foot. King's foot. Things like that. Now we codified an inch was your thumb. Things like that. A yard was like from your nose to the end of your hand. You know, like this is a yard. Now, if I was selling stuff, selling yard goods, I'd be in trouble, wouldn't I? Because I'd be selling a lot of yard goods. I'd probably want to hire a midget because their yard's going to be a lot smaller. Things like that. You know, so, but also things like an acre. An acre. Yeah, you see signs around 53 acres ready for development. It's like, what is an acre? Well, an acre is just a measure of land, but originally, an acre was how much land 2 oxen could plow in 12 hours. That's what an acre was. You know, things like that. But even in this, so we have 12 inches, okay, 12 inches to a foot. All right. 3 feet to a yard. All right. Next one's like a mile. But what mile? You know there are 2 miles? You know there's 2 different miles? There's statute miles, which is 1,760 yards, which is what we use when we drive around. When you drive 10 miles on land, you use a statute mile. But there are nautical miles, which are 2,000 yards, which are actually 1 minute of latitude. 1 minute of latitude. You know, we measure distance on the face of the earth, latitude, longitude. You have your little GPS thing, you put in the latitude, longitude, and all that. But 1 minute, which is how you break up a degree of latitude, is 2,000 yards. But even in land measurement, you have things like furlongs, you have rods, you have leagues, you have fathoms. That was one we used in the Navy. Our charts were laid out in fathoms. How many fathoms? A fathom is 6 feet. We measured chain on the ship in something called a shot. Shots of chain. How many shots of chain do you have on the bottom of the ocean? Because it's the chain that holds your ship in place when you anchor out. The anchor just helps you get it out. And a shot is 15 fathoms long, so 90 feet. So if you had a shot of chain out, you had 90 feet of chain out. Things like that. Okay. Okay, we'll come back. So let's go back to our, it looks like our thing here is kind of bubbling and stuff like that. But we'll let, looks like it needs a little bit more water. Drain it, open it. Yeah, I am not eating that. You do not want to eat, you know, glassware. If you're eating things, usually you have a set of glassware that's only for eating stuff. So put a little bit more, let that cook a little bit more. Water went away. It's kind of like me making oatmeal and stuff like that. Oh, wrong thing. All right, so just think. Also, just ounces. You know the 3 different kinds of ounces. 3 different kinds of ounces. You have fluid ounces, your juice box. You have regular ounces. You know, 16 ounces to a pound. You by dry measurement. But there are also troy ounces, which we measure like gold and silver in troy ounces. There are 12 troy ounces to a pound. 12 troy ounces to a pound. Very confusing. You like using this? You want to have to convert all the time with this? No. So we don't use it. So in the 1700s, there was a group of French guys. Now, I don't know, maybe it's because they didn't want to use the English system. You know, the French and the English, they don't really get along very well. But these French guys said, hey, I do not want to use this system. I don't know what their reasoning was. But they wanted to develop a system that we now call a System International, the metric system. And it was developed as a complete system. And they start with a meter. Meter. You wouldn't know
Is that a yardstick? Oh, sorry.
it's okay. But you have a meter stick. You start with a meter. Oh, they're over there in the corner. Still learning the room. Thank you. So, you know, did they go out and just chop down a tree and say, this is a meter? Is that what they did? Well, they could have, but they didn't. They actually said, okay, we have this thing called the Earth. We have the North Pole. We have the equator. We have Paris. What Paris? What nationalities, guys? They're French. Paris, right? Paris. Okay, so we take a line. We're going to go from the North Pole to the equator. We have this distance. So if we travel from the North Pole to the equator, and the line goes to Paris, and I'm going to break that distance into 10 million pieces. I'm going to break that distance into 10 million pieces. And guess what? I get a meter. So a meter is 1 meter is 1/10,000,000th of that distance from the North Pole to the equator on a line that goes through Paris. That's where it comes from. Now, if you looked it up today, they would say probably something like so many wavelengths of a certain frequency of a certain color of light from a certain element, that's a meter. We get more refined. Actually, every country has their own standard meter. You know, in other words, somewhere in their weights and measures, you have a standard meter. Even in the United States, we have a standard yard and we have a standard pound. It's these usually very fine measurements and things like that, and they're kept under sealed control. In the United States, they are kept at the Naval Observatory. Naval Observatory is in Maryland on that. Anyone knows? Any of you know who lives at the Naval Observatory? There's a government official. His official residence is at the Naval Observatory. So somebody who does usually he's a tiebreaker. Tiebreaker. The vice president. The vice president lives at the Naval Observatory. That's where the vice president's home is on that. Now, the vice president's job, among other things, is to do the tie. If there's a tie in the Senate, he does the tie vote on that. So they keep those weights and measures on that. So they have a meter. Now, they broke this meter into 10 parts. Now, remember, the prefixes in this system are in French. They are in French. Okay? So that's why, you know, one thing used to confuse me when I was a kid, when I first learned this. And, you know, milli. Why is a milli a million? Why is that a millionth of a meter? Well, milli, because mil in French means 1,000. Milli, 1,000. So these words come centi, cent. Same word our word cent comes from, 100 cents. Centi, 1/100th, and things like that. So they break it, so it's a base 10 system. It's a base 10 system. Why do we like base 10 systems? Certainly English is not a base 10 system. Why do we like base 10 systems? What's our county system? Well, what's our county system? It's base what? We use it, when you go to math class, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a base 10 system. It's our county system, so we made it base 10. Most of us have 10 fingers and toes. Some a little more, some a little less. You guys do know this is a recessive gene, right? Did you learn that in biology, that this is actually a recessive gene? You know, 10 fingers and toes is a recessive gene. I know in biology you tend to learn that, you know, that dominance is going to be up here, but what does that tell you? How often does the dominant gene, which is 12, by the way, the dominant gene is 12 fingers and toes? How often does that actually appear in the population? Very rare. Very rare. And usually in Western countries the last digit is taken off surgically when a baby is born like that. Taken off surgically because it doesn't work very well. Although a friend of mine sent me a picture of a girl from Thailand. We used to see, you know, my roommate from the academy. And he said, look at her hands. And if that's something that looked weird, it's like 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10, 11, 12. She had 6 fingers on either hand. Because she was in rural Thailand where they didn't do things like that. Alright, so it's a base 10 system. Volume. Now, from length we get volume. Volume is not a derived unit. on that. It's not a derived unit. So we have volume on that. So what they did, they said, okay, we're going to take a box. And it goes 1 centimeter by 1 centimeter by 1 centimeter. And we know volume is going to be 1 centimeter times 1 centimeter times 1 centimeter. 1 centimeter cubed. 1 cubic centimeter. That is volume. And we're going to say that 1 milliliter is 1 cubic centimeter. This is where we get our volume from. This is where we get volume from. The 1 cubic centimeter. This is why there is no SI unit, because the true SI unit is addressed in how many, a distance cubed. Okay, liter is not an SI unit. The thing is, to get a liter, 1,000 milliliters is 1 liter. And you might say, well, that must be a meter cubed, 1,000, right? 1,000, but it doesn't really work that way, because that means 1,000 centimeters cubed. Well, what is the cube root of 1,000? What times what times what is 1,000? 10. So we have 10 times 10 times 10. And these are centimeters, and 10 centimeters is 1 decimeter. So that 1 liter is actually a decimeter cubed. Now, I mention this because here in physics, the decimeter cubed is our unit of volume. But a decimeter cubed is a decimeter cubed is our unit of volume. We don't use the liter. When you see some of our units, when we get, especially we talk about gases and things like that, if you see volume, you might see our when you look up the constants and things like that, you would see decimeter cubed. You generally would not see liter. But just remember, a liter and a decimeter cubed are the same thing. It's a little box about this big, a decimeter cubed. In physics, we actually use the meter cubed as our unit. Big thing on that. All right. So questions? All right. We'll come back to that. So let's go back to our demo. So right now, some of you have noticed the smell. That's an observation. You should write that down. You should write down what do you smell on that on our thing. Now, one thing about total. Total has lots of what in it. It's known for what? You get the commercial. A lot of fiber. Also, a lot of cereals, they put a lot of what in them, a lot extra what in them. They put calcium, they put another mineral. Starts with an I. Iron. This worked out. Let's see. If I can find. Taking a little. There it is. See if we got any. And it didn't. Oh well. Story of my life. Maybe I'll click. I'm supposed to collect up the iron in here, so maybe I'll swirl it around some more. Let it swirl some more. Maybe I'll collect it. And we'll see. We'll let it wait. Story of my life in demos. So we'll come back to that. The amazing thing in here is if it will not be that my demos don't work. Actually, the amazing thing will be the demo actually works the way I want it to. Okay, so let's continue this. Volume. So from volume we get mass. Now mass is based on water. So these guys remember. So now they have a length. They have a volume. Now we have mass. We want to know how much stuff we're buying. And mass is how much stuff we have. How much matters. Now weight. Mass and weight are different. Although you need to know the mass to find the weight. Weight is how much gravity pulls down on a mass. It's not the same thing because your weight will change as you go to different places in the universe. But mass is always the same. It's based on a certain volume of water at a certain temperature. And this is pure water. Why would you pick water? Why water? Well, how hard is it to get water? Not very. Though it's very common. I mean, could they have used some very rare element to make their standard? Yeah, but then it'd be hard for other people to actually do anything with it. It'd be very hard. And so we have 4 degrees C water. Not only is it pure, we have to have 4 degrees C water. Anyone know what property of water is a maximum at 4 degrees Celsius? Anyone? What property? There's 2 of you that should know this. What property of water is at a maximum at 4 degrees? And water is still a liquid at 4 degrees Celsius. Water is still a liquid at 4 degrees Celsius. So what property? Anyone? This is why ice, solid water, floats. Water is the only substance where its solid will float on its liquid form. In all other substances, its solid form will sink to the bottom. This is a unique property of water. One of many. By the way, water is the most unique substance on the face of the earth. Water does things that no other substance does, and it's why Earth doesn't freeze up into a little ball of ice. Because if water didn't do what it did, the oceans would be mostly frozen because of pressure. Just from pressure alone, the water would be frozen, but also on the surface, water is densest at that. This is why it is. When you go out and look at one of these big ocean liners, what can you say about its density compared to the density of the oceans? Higher or lower? It is lower. How do you know that? It's floating. If it was denser, it would sink. And that's the whole idea on a ship, is you want to make sure your ship is always less dense than the ocean, because it gets very bad when it gets more dense. On that. So water is densest. So they said 1 milliliter, a cubic centimeter, or a cc. You get medicine that says take so many cc's of this medicine. Cc stands for cubic centimeters. So your medicine is actually measured out in the metric system. If I take 1 cubic centimeter of this water at 4 degrees C, it has a mass of 1 gram. So 1 milliliter of pure H2O at 4 degrees Celsius has a mass equal to 1 gram. Is this an arbitrary thing? Is this arbitrary? In other words, is there any reason why we have to say that is? In other words, could we have used any other material for that and said 1 cubic millimeter of gold is 1 gram? Could they have done that? Yeah. They chose water. Okay, so this is an arbitrary thing, but this is what all other masses are based on. Our balances, when we balance something, they're basing it on that amount of water. When you have a balance, the old-fashioned, why is it called balance? Because that's what they used to be. You used to have 2 little pans there, right? You put your thing on one side, you put little masses on the other, and when it balances, you know that they're equal. Why do we have that term balance on that? A scale measures weight. A balance measures mass on that. All right, questions? Questions? All right, let's see if our demo is cooperating here. Not going to be cooperative today. Now what this was supposed to do is this should have come out black, because this is magnetic. And what they put in the cereal, that when they add iron to the cereal, they just powder up like iron and throw it in the cereal. So you should have seen some iron. The idea here is that in your iron, when they add iron to your food, they are adding honest to goodness iron. Just they grind it up into a powder, and they do that. And they in your body, as you digest it, some of it actually goes into your system because you need ionic iron, not metallic iron. But your digestive system changes that. So write up a conclusion of what you saw, what happened here, and it's okay that it failed. You can say it didn't work, and blah blah blah. I mean, I have no problem with that. It happens. Story of my life. But I did want to show you guys our things from last time, that first day. Some of our little things here. There we put the thing into the glove. So there we put that polyurethane stuff into the glove here. What? There's the stuff. To be honest, they don't say what the chemicals are that are in the thing. They send it to you made on that. I'm going to get that up there so you guys can pass it around. On that, you can see, just kind of filled up the whole hand. We also remember the I put the styrofoam cup in the acetate. That's what's left, or the acetone, like it's stuff used like nail polish remover. That's what's left of that styrofoam cup. On that. See what it. So what happened to the rest of? What happened to the rest of the cup? No, so there's no liquid. By the way, I did not empty any liquid out of here. So what happened to the liquid in here? Evaporated. Yeah, it evaporated away over time. And it carried away the rest of the cup with it. In other words, it was bonded to the liquid there. It took away the rest of the cup. So there's very little of that mass. Now the mass went somewhere, but it went out in other places on that. All right, so question about where our metric system comes from. We're going to talk briefly about SI units and some scientific notation on that. What? That was the demo. Didn't work. We'll see it. We'll look at the back end of the period. I'll actually let it run. Maybe if I put it a little slower. Oh, I'm sorry. I'm going to slow it down some. Maybe turn it too fast. Let it run like that. All right, so SI units. Okay, some of the things are base units. You got to remember we have dimensions. When we talk about other units in this, when we have the units of energy like the joule and the dyne and things like that, they have other units in them. So we always have to make sure we match it. If the unit has a centimeter in it, we have to make sure all the measurements are centimeters. If the unit has a meter in it, make sure it's in meters. That's what the big thing here. We have our dimensions. I'll give you a watt. When you go to the store and buy a light bulb, a watt, and a watt is a measure of power. Now, when we say 1 watt, what we're really saying is 1 kilogram meter squared per second cubed. And that's really what a watt is. You know, if you did the calculations. So this is why masses always have to be in the right thing. They have to be in the right amount. You know, mass has to be in the mass. The distance is the right distance. Time, and things like that. And we need more time. By the way, if I get too far ahead, it's okay to ask you to slow down a little bit. Maybe I need more time on this slide.
Yes.
We good? Yes, sir.
How was your weekend? What?
Remember I mentioned my wife going to the emergency room on Thursday? Well, we end up back there again on Sunday. Meds are working, but we don't know exactly what happened on Sunday. Well, she either had was a thing that's like a little, like a mini stroke. It's a transient thing. Could have been a migraine, could have been dehydration. We don't know. Didn't get to go camping, which is what we were going to do this weekend. We usually go to scout camp on Labor Day weekend with all our friends. Boy Scout camp in Willits. Willits is way up north. What? Willits is north of Utah. It's about 120 miles north of San Francisco. Boy Scout camp, no. You sleep on platforms. Because everything's handled. But there's lots of activities. You know, you have archery, there's a lake, there's things to do. You know, kayak, sailing, all kinds of stuff, swimming, horseback riding. No motorized craft on the lake. Well, it's not a very big lake. All right. So, metric conversions. Now, we will have to do some metric conversions. There's times when you measure centimeters, you're going to need meters. There's times when you have grams, you're going to need kilograms. And generally, you know, we'll do some. I don't usually, chemistry is a CGS system, so we don't have to do a lot of conversion, but there will be times when we use units that do require some conversions from one thing to another. Now, the thing to remember is that the base units are things like meter and liter and gram and newtons and dynes and seconds and watts and things like that. Those are what we consider base units. And base units have a power.
Yo, you okay?
Yeah, that's the poor guy. They're 10 to the 0 power. Whoever designed this room did not put power in the right place.
I know. I put a carpet over there.
Well, there's a power thing in the bottom that keeps you from tripping over the cord, which I just did.
It doesn't work.
I think I move around a lot more than you think. So 10 to the 0 power. Now anything to the 0 power except 0. You know, any non-zero number to the 0 power always equals what? 1. So 10 to the 0 power is 1. 10 to the 0 power. And these are all base 10 conversions. Now each prefix is a power of 10. It is a power of 10. And the way to convert to the base unit. So like we're going from centimeters to meters. Megawatts to watts. This is a system you can use. You can just tack on that power of 10 in scientific notation, Matt. Things like centi. Centi means 10 to the minus 2. That's what centi means. It has a power of 10 to the minus 2. So that if I had 15 centimeters and I want to know how many meters, all I would have to do is tack on that 10 to the minus 2. So I get 15 times 10 to the minus 2 meters. However, is that proper scientific notation? Is that? No, it's not. But I want to ask you something. If you plug 15 times 10 to the minus 2 into your calculator, would it work? Yeah, it would. So when we're doing calculations, a lot of times if you just plug in these conversions, your calculator is going to put it back into proper scientific notation. However, to do proper scientific notation, remember we would have to take our decimal and move it one time that way. And it's 1.5 times 10 to the minus first. Because if we move to the left, you might make a note of this, when we move the decimal to the left, we add to the power. So negative 2 plus 1. We moved 1. If you have to move your decimal point to the right, you're going to subtract. from the power. All right? We'll go back to your inner algebra. This is covered in your algebra classes on that. But other prefix. Now, generally, for something like centi, you're probably not going to do this because you just move the decimal point. We have another way to do that. But what if we had something like nano? Nano is 10 to the minus 9. You measure wavelengths of light in nanometers, especially visible light. You guys, we all see in a spectrum of about 400 to 750 nanometers. Those are the wavelengths of light that you can see. But you might have to convert that to meters on that. So again, if I had that a frequency of light of 720 nanometers, that would equal 720 times 10 to the minus 9th meters. But again, is that proper scientific notation? No. Right now, you guys, put that in proper scientific notation and see if you come up with the right value. See if you move right. Remember, left we add, right we subtract. Let's see if you can get the rest. So everybody try to put that back in the scientific notation. But again, I can put that number into my calculator and it will work. So, can someone tell me what should this read? Now, first of all, the number. What should I, for proper scientific notation, is 720 acceptable? No, it's supposed to be what? Well, where is the decimal point supposed to appear in a scientific notation? 7.20. So this should be 7.20 times 10. Well, I move my decimal point 2 times to the left. -7th. Yeah, it's going to be -7th meters, right? Because we add. We move to the left, we add. If we move to the right, we would subtract. So we're adding that. Questions? You know who I'm talking to. Questions on that? So again, this works when you're going to the base unit. But sometimes, like gram to kilogram, if we have to do a gram to kilogram, this doesn't work on that. So we have another way to do that. And that's the stair step, which you guys have probably seen before, hopefully in your other science classes, the stair step. And the stair step is good for doing basically from millimeter to kilo. So milli to kilo is what this is good for. Really, so you don't really have to use that other system. And it's foolproof and it always works. Anyone have my hand? Anyone have the little piece, that little round piece? All right. So, it's another way to convert. Now, on the stair step, we usually draw 7 steps. And every step is a power of 10, but you can always extend it out. I mean, these are powers of 10. Every time you go a step, it's another power of 10 on that. The decimal point is always at the end of the step, and it moves the same direction as you do with the stairs. You always write the stair step high on the left, low on the right. On that. Anyone need more time on this slide? Everybody good on this? So let's draw our stair step. And remember, 7 steps. We start up high. 1, 2, 3, 4, 5, 6, 7. 7. We have our decimal. The decimal. Right there. It moves left or right. In the middle, we have our base units. Remember, our base units are 10 to the 0 power. They represent 10 to the 0 power. This would be like meter, liter, gram. It could be a watt. It could be a second. It could be a joule. It could be an erg, and so on. Different things. Whatever it is, that's the base unit, 10 to the 0 power. Going down, we have deci, which is a lowercase d. We have centi, a lowercase c. milli, which is the lowercase m. And it's very important you have uppercase and lowercase on these because you might be doing the wrong unit. A lowercase d, a lowercase m means something different than an uppercase d and an uppercase m. But deci, 10 to the minus first. Centi, 10 to the minus second. 10 to the minus third. If I extended this, 3 more down would be micro. 10 to the minus 6. 3 more down on that is nano. 10 to the minus 9. We don't need that. All right. Now notice also the ones going down, all the negative ones are lowercase. There's one exception to that. But if you see a lowercase letter, you should be thinking negative power. There is one exception you have to remember to that. But all of the lowercase ones except for one are going to be negative power. Going up. Deca, capital D. So you can see there's a difference. Little d, big D. Little d is deci, big D is deca. Hecto. Kilo. And so kilo is 10 to the third, 10 to the second, 10 to the first. Going up, all positive powers of 10 have a capital letter, except one. But you know, if you see a capital letter, it is a positive power. If I went 3 more up, I would get to mega, capital M, 10 to the 6th. 3 more up of that is capital G, giga, 10 to the 9th. 3 more above that would be capital T, tera, 10 to the 12th. In fact, some of these letters, that's what these things mean, like a gigabyte. I have a 500 gigabyte drive. It means I have 500 billion bytes. A terabyte drive would be 1,000 gigabytes, or 10 to the 12th bytes. Things have improved. I mean, my first PC had a 40 megabyte drive. That was considered very large back in 1990. 40 megabytes was a big drive. I have programs bigger than 40 megabytes now. You know, so things were a little different. When I first started using PCs, it was before Windows. You know, things like that. So on this. Now our one exception, Mary said there's one exception to the lowercase. Kilo is the one exception. Kilo is the lowercase. It's not an uppercase. It is lowercase. It is positive. So this is the one exception to the upper and lowercase rule. How do we use this? I mean, is there anyone here who's never seen this before? Hoping, yeah, you've all seen this before, so you know how it works, right? We just move the decimal point. So if I had 53 grams, and I want kilograms, right? I'm going to start here at grams. I move to the left, 1, 2, 3 spaces. So I'm going to take my decimal point. 1, 2, I need 3. What do I do? Add a 0. Yeah, right. If I run out of 0, so that becomes 0.053 kilograms, like that. All right. So this is not mystifying, right? You guys can all handle this. Good thing you guys have put in your planner. Good thing just to have the planner available and things like that real quick, along with everything else. Yeah, you guys all found your periodic table in your planner too? Yeah, I'm not wild about how they label some of it because just metals, non-metals, gases, and things like that on that. All right, questions? Questions? On that. All right, so before we get started here, because we're going to be doing some of these things, what I want you to do is come grab one person from this group. Remember, you're numbered 1, 2, 3, 4, 5, 6, 7, 8, right? It's your groups. Up here I have a cart. Basically, a lot of times when we get our equipment, we'll have little things. So this is group 8. You have some equipment. Some of you are responsible for this equipment. When it comes back with all the equipment, things like that. So what I want you to do is grab the kit here and just grab a piece or two of scratch paper and just bring it back to your station for now. Also, you need to get out a separate sheet of paper. We're going to develop our first lab report, but we're going to go up piece notes. You're going to take some notes, then we're going to work on a lab report. We're going to take some notes, we're going to work on a lab report. You also need that packet on lab reports. That's what we're going to work on now. So all those things. So one for grab the kit, grab a piece or two of scratch paper on that. So whatever number you are.
I forgot what number it is. I think it's 6, right?
You would be group number 7. You're group 8. Actually, this would be a good time for you to run off and go.
Yeah, I was just going to ask that. What would I be?
So run.
And what would I be?
Where are you? Where do you sit? Right there. That was group 4. Where are you? What? Back there. So you'd be group number 5.
What about that middle?
Right here? You'd be group 3. Yeah. Oh, so you guys here. So group 6, that is you guys. Right there. Christian, that's you. Takes a while. Some of the guys who have me for physics, they're used to things like Michelson and Newton, and they're used to science names. So
You don't know.
I don't really have that opportunity to rename everything here.
All right.
That'd be old school here. Okay, so we are going to talk about scientific method. Now we do have our lab sheets. That lab packet is something you want to keep safe on this. The lab. Now notice the front page says formal lab report. We are not using that. Turn the page. We are going to be using what's called the in-class lab report, and it really follows more closely with scientific method. We're going to see how this really matches up with scientific method. And we'll talk about this. It kind of tells what each section is, as we're going to do this little lab today, and probably we'll finish up next time on that, because we're not going to finish everything today. But it also talks about like writing conclusions. Like you can go back to your own seat for now. Whenever we do a lab, basically the front table will turn around and work with the back table. That's the easiest way to do that. It's so we don't have to move around and things like that. We just front table will turn around when we get to that point. Conclusion is your own. You guys, all you do, you guys are going to have your problem, your hypothesis, and your data, and your calculation. You work together. That's okay. You get to the conclusion. Everybody writes their own conclusion. There's that plagiarism thing. Everybody writes their own conclusion. And there's a section here that's little prompts to help you do the sections. There's a bunch of elements. Kind of gives you some ideas how to do those various elements on that. There's a little checklist. This is more of the formal lab, but really what you're going to knock out is the procedures and materials. That's what gets knocked out of the in-class lab on that. It has a sample formal lab. It also has a sample of what the lab should look like when it's all put together. Now you guys could be doing class to be handwritten. Mine's typed just because that's how to get electronic. But yours could be handwritten. So on that. But it gives you an idea how everything's supposed to look when it gets all put together. Your proper graphs and all that stuff. If we ever make something, diagrams. If we make something in class, there's a diagram. Not so much a chemistry thing, more of a physics thing on that, and general science thing. It's really the same lab format for all of them. But scientific method. By the way, is science the only ones who use scientific method? No. Do the other people call it scientific method? No, they don't. Business, you call it a marketing survey. But they use the same procedure, marketing survey. They have a problem. We want a new product. McDonald's, they want to make a new product. So they go out and they have a hypothesis. We think this new product is going to do that. They test it. They make some procedures. They do small group analysis. They do big marketing trials. I can say when I was in college, there was, went to New York City. In my freshman year. Just took a few days, went to New York City on that, and went to McDonald's, and they were selling this turkey or the steak sandwich. Okay, for McDonald's. But when I went home here to California, it wasn't on the menu. It didn't exist. But basically, what they were were test marketing it in New York. They took different areas, test marketed on that, and that one failed. Actually, that one never came to the market. After a while, you didn't see it on that. You didn't see it in Maryland either. It was something that wasn't on the menus in Maryland. Although McDonald's, from where the college was, because we walked everywhere, the only fast food place that was near our college was actually a Burger King. They made a lot of business there. They were like the only fast food thing in walking distance of the academy. Do you have a question? No. All right, so basically we have 5 steps. And we start with a problem. We always start with a problem, which is our question. We have a hypothesis, which is the answer to that question. we perform an experiment on it. We analyze the data, and we come to some sort of conclusion. Now, we are going to expand on each of these. We will expand on each of these as we go along. Okay, so we will be expanding on that. Do we need more time? So we have our educated guess, provable and disprovable. But disprovable, but we're going to go on to the next slide. Anyone need more time on this one? Right here. Everybody got this? We haven't got to the lab part yet. We'll come back to the lab. We're taking notes right now. This is notes. Alright, so the hypothesis must not only have a way to be proved. Obviously, we have no way to prove it. It can't be a hypothesis. But more importantly, there has to be a way to disprove it. Does that mean you want to disprove it? No, but there has to be a way to disprove it. An example here. If I said, there is life on other planets. Well, again, this is an educated guess. I mean, certainly we have discovered materials that could produce life in other places. There's water on Mars. However, I go to Mars and don't find life. Does that disprove my hypothesis? No. The only way to disprove the hypothesis, how many planets do I have to visit to disprove the hypothesis there's life on other planets? What? All of them. Every single planet in the universe. Can I do that? Well, that's our solar system. So we're telling you, we have to check every planet everywhere. Yeah. Really, you can't. So there's no way to disprove it because we don't know we don't even know where all the planets are. But what if I said this? There is no life on other planets. Is there a way to disprove that? Yeah. Find life. Does that mean I'll ever disprove it? No, but there's a way to disprove it. That's the point here. There has to be a way to disprove your hypothesis. A way to disprove it. Not that you are actually going to disprove it, but there has to be a way to disprove it. Okay, on that. And that's what we mean. So, for your labs, anybody need more? Just don't worry about this part yet. Everybody got this top part in? We got the top part? We'll come back to this. If you got that, that's fine. We'll come back. So, our next part, our hypothesis. Now notice, if you look on your sheet, look on your lab sheet. We look on here. It says there are two elements to our hypothesis for lab reports. It has the answer. It's the answer, and the answer is just a statement that answers. It's not if the statement just answers the problem. And a reason why you think that's the answer. So remember, our problem is, which is a long or short wingspan going to fall faster? And so you want answers. There are actually three possibilities to that. Long wingspans will fall faster. Short wingspans will fall faster. Or the third option is, it doesn't matter how long the wings are. They're all going to fall about the same rate. So you want to discuss with your group what answer you want to come up with and a reason. This could be one or two sentences. So right now, everybody consult front table, consult with your back table, come up with a consensus on what you guys want to do for your hypothesis, and write it down with a reason. On that. So let's look at a couple of things about hypotheses.
Instead of getting a small diagram that we worked out, my original idea is that I wanted to fling somebody over the road and land them in the next door neighbour's garden, which is quite a large one, and hopefully it would be a soft landing.
Guess he knows what he's doing. But surprisingly, Denham's specifications are off.
I didn't really have any idea how it was actually going to work. I don't think that worked. In retrospect, we probably should have thrown something else other than human.
That human was Lonnie Hilgendorf.
I thought it was a great idea. Great way to spring a thunder. Very final words to me were bones feel like glory.
I think adult beverages were involved in this.
Can't really argue with that.
Adult beverages were involved in this.
Looks like logic prevails.
Alright, so remember his problem was he wants to fling a human being across the street into the neighbor's garden. How many of you think that he's going to succeed with this young lady on getting her all the way to the garden? How many of you think? Raise your hand if you think your hypothesis that he is going to get it all the way across. How many of you think this is going to end badly for the girl?
And so does physics.
The ground really hard.
Glory is forever. Or at least until you've regained your senses. With Lonnie healed and Denham unfazed, it seems likely that he will catapult again.
I need to see human beings fly through there, but next time will be a little bit more padding.
More padding shouldn't be hard to get. But Denham might have trouble finding a new volunteer.
Okay, so alright, we're going to watch this one. Now some of you have probably seen this one. This was a viral video a couple years ago. Now this was actually, I think, Microsoft or somebody. This was their ad, part of one of their ad campaigns in Europe. The guy isn't speaking English, by the way. If you can't understand him, it's because he is not speaking English. Alright, so let's watch, we're going to watch this again, and what I want to ask you guys in this is your hypothesis. Do you think this is real or a special effect? How many of you think this is real? How many think it's real? How many of you think it's a special effect? Well, let's watch it again. And there's a part that really gives it away on whether it's real or a special effect. And see if you can identify what it is. Not sure why it's running so choppy. Okay, real or special effects? And the answer is actually when it hits the water. How much of that? I mean, you guys have used these little things before. How much do they move around? A lot. This guy, when this guy hit the water, do you think it would stay on that platform? No, he'd knock out the platform. He'd probably break his legs. Probably put him right to the side. Yeah. By the way, this is a special effect. This was admitted. They did admit it that it was a special effect. It was all special effects. However, if you watch Mythbusters, they did do this. Now, they used the lake, but I think they found they had to use a much bigger hill. To get the results that these guys did, they had to use a bigger hill. But they were able to fling off the thing and hit the target. They used the lake, though. And they did send Adam. Adam's the one who did do it, but they used the lake. And I think he did go a lot deeper than that pool. There was no way you would be able to use just that pool. They used their landing spot was a lake, but they did do that. But these guys did admit eventually that it was a special effect. No. All right. It's one of those do not try this at home things.
According to legend, a really good glass of prayer should be able to bring down a house of straw. Let's see how it goes with an explosively generated vortex ring.
By the way, this is an example of a badly designed experiment.
It's the first time it's ever been fired, and with 150 litres of one of the world's most explosive gas mixers in there, I'm not even sure that this is really a safe place to stand. Seems about right. I'm going to need these, I reckon. 3, 2, 1. Oh, yes! Call me hopeful, but there was definitely something there. But was it a vortex ring? Filmed at 1300 frames per second, there is no doubt. But the ring you can see is not a smoke ring. It's formed by the pressure drop within the vortex, condensing the water out of the damp air above the lake. A 200-mile-an-hour cloud. Bring on the sticks and bricks.
What story is he talking about? 3 Little Pigs.
3, 2, 1. Whoa! Yes! Fantastic! Well, it makes mincemeat of a house of sticks. Bring on the bricks.
Alright, so I want you to... How many of you think he's going to knock down the house of bricks? This house of bricks. How many of you think he's going to knock down the house of bricks? How many think the bricks are not going to fall down? Now the question, look carefully at these bricks. What do you notice is missing? The cement, the mortar. The mortar. Does that change your answer, those of you think it's not going to get knocked down? The fact that they are not mortared. Okay, so let's think about this.
Even in fairy stories, they couldn't get a blast of air to knock down a house of bricks. We're heading into the world of the unknown a little bit.
Today in Mythbusters, they would have actually mortared the bricks.
Changing the elevation on it, changing the gas mix in there, see if we can get a perfect gas mix. So that's just the right amount of molecules of acetylene reacting with just the amount of molecules of oxygen in the air. So there's no passengers in there, it's got to be all explosive. Let's see how that goes. Three, 2, 1. Hey! Yes!
By the way, did you notice, what do you think was bad about that particular experiment?
Incredible!
Where did he aim? The top. Was he aiming at the top of the other two? No. Do you think if he actually aimed, now aim at the top, which is probably the weakest point, didn't hardly but barely got to tip over. If he had aimed toward the middle, do you think he would have knocked it over?
No.
No, probably not, and definitely not good. So I also put that up as an idea of a bad experiment. That was a badly designed experiment on that. So let's just hope he kept flipping over. An experiment. So that leads up to experiments. So we're gonna probably be doing more, but we need to talk a little bit about the experiment. So we're back to notes. We're back to your notes. Experiment kind of has several parts. In the experiment, you are making your procedure. After we have a problem hypothesis, you have to make a procedure. You have to figure out what materials and what data you're going to gather. You're going to have to practice it, and finally you're going to run your experiment. You know, it's a good idea to practice your experiment before you do it. Is that a good idea? Yeah, especially what if your experiment only happens once every 10 years? You want to make sure you know how to do it, right? Also, if it costs you $10 million to do one trial. You laugh. There are experiments that cost. They're very, very expensive. I mean, I'm sure when they do an experiment out here at Slack down here, I'm sure it's pretty expensive. That's a lot of electricity they have to use for one experiment to accelerate those little particles down there. Anyone need more time on this particular slide? Anyone need more time? Raise your hand. More time. Okay. So, we're going to expand on those. Procedures. Procedures are the experiment. The experiment's procedure must be written. We write down step by step of what we're going to do. We're going to determine what data we're going to gather, the data tables. Now, in your lab report, really it's only the data table part that we have. That's the observation section. So the observation section is our experiment, is our conducting the experiment part. I mean, you'll have a procedure sheet and things like that. Materials. Well, the materials are based on what the procedure identifies. You know, how many beakers, how many computers, what programs you need for your computers, things like that. And materials and other equipment, you're going to need to gather it up. I gave you a nice little box that has your materials, right? You had to come up, you had to gather your materials to go back to your seats on that. Anyone need more time?
Yeah.
So, one more part about materials. Any apparatus we need to construct, if we have to construct something, we construct a linear accelerator down Stanford. I mean, when they want to do experiments, you know, doing that, they had to go out and construct a linear accelerator. Okay? Things like that. Practice. We dry lab it. In other words, we evaluate. Also, we can determine, are we actually collecting the data? Are we actually doing the things we think we are doing? The trouble is sometimes we have an experiment that really isn't proving what we think it is. Okay, so that needs to be addressed on that. And we need a little more time. Raise your hand. Now we need to run our experiments. We run the experiments, which means we gather our data. We have quantitative and qualitative data. Quantitative is what you measure. In other words, it's the numbers, the things. I measured a certain length in this whirligigs exercise. You're going to measure a length. You're going to measure a time. You're going to measure a length and a time. You know, how the wingspans. You're going to measure how long it falls down. Qualitative are your other senses. What do you see? What do you feel? What do you hear? Remember, what do you smell? Remember, in our little demonstration, we had a smell. We smell, we have that smell. Taste, although rarely do we use taste. Although in geology, there were some minerals that you actually identified by taste, like the mineral halite. Halite is actually salt. So it's identified by taste. But we try not to taste things in lab because we do not want to get poisoned. Remember the toxic Twinkie. Also, qualitative observations. Things that might affect the outcome of your experiment. You know, if you broke something, if you were using a thermometer and it got broken, thermometers get broken, and you got a new thermometer. Not all thermometers are the same. It could affect your data. Not that it will, but anything that might affect your data, you want to make a qualitative observation, and we try to repeat our experiment as often as possible. We're going to repeat as often as possible. Okay? We have just about enough time to make our data tables. So we're kind of done with notes. So remember, at the end of note taking, we need to make that paragraph summary at the end. Actually, why don't we do our paragraph summaries now? Because I know that clock is a little slow. Let me check what my clock says. I have 10:30, and I know that's a minute behind.
This one is pretty good.
That one's like, yeah, I looked at it when the bell rang before. I was a minute behind on my computer. So we have about 4 minutes left of class. So right now, what everybody needs to do is write your summary for everything we've done today. Keep your lab paper safe. Keep the thing we've been starting safe. Remember, homework tonight is to read out of the book, sections 5 and 6, and a little bit. There's a summary section there on that. What? No, you had 1, 2, 3, and 4. But if you did 5 and 6, leave me a note in there that you did them all together. Because last time the assignment was 1 through 4. That was the in-class assignment. If you finished it in class, you turn it in class. If you didn't finish it, you're supposed to finish this homework.
Oh, well, I finished it. How?
You finished it here. Then you turned it in.
No, I have it right now.
Well, throw it and just put it in the box.